pleasure to welcome you all for this international webinar. In this occasion, I would like to acknowledge my deep sense of gratitude to our beloved principal, Dr. S. Vanati Madam, for her constant encouragement and support. Since she is engaged in urgent official work, she couldn't join with us now. She has sent her wishes to us for conducting this webinar successfully. Thank you, ma'am. Next, I wholeheartedly welcome our resource person of the day, Dr. S. Thayumanavan, Distinguished Professor, the Department of Chemistry, Massachusetts University, USA. He will be delivering lecture on inspiration from nature, responsive materials for modern world. Sir, surely your talk will inspire all of us. Again, I welcome you, sir. It gives me immense pleasure to welcome all the faculty members of my department and my college. With equal pleasure, I welcome all the faculty members from various colleges and various universities. Next, I extend my warm welcome to all the students participants. It gives me pleasure if I welcome you all once again. Welcome you all. Thank you.
Thank you, Madam. It is my honor to introduce Dr. S. Thayumanavan, Distinguished Professor of Chemistry, University of Massachusetts and United States of America, who is an outstanding researcher. He is also the Director of Center for Bioactive Delivery at the Institute for Applied Life Sciences at University of Massachusetts. He received his BSc and MSc in American College, Madurai. He received his PhD from the University of Illinois in 1996. Following his postdoctoral stint at Caltech, he started his independent career at Tulane University in 1999 and moved to University of Massachusetts in 2003. Dr. Thayumanavan lab is interested in translating the novel polymer-based molecular assemblies to make an impact in biomedical and sustainability application. His group develops fundamental design guidelines for self-assembled systems which responds to specific cues. These guidelines are used in enabling the applications in variety of areas, including self-healing materials, autonomously functioning systems, drug delivery, intracellular delivery of biologics, and cryptic catalysis. His work has been resulted in two peer-reviewed publications in high-impact journals. The innovation in his work is also produced nearly 20 patents and patent applications. Dr. Thai has received numerous national and international recognition for his creative contribution. He also launched an early-stage company based on technology developed in lab to solve complications based on liver diseases. We are blessed to have such an outstanding researcher in our webinar for delivering a lecture. Thank you, sir. Kindly proceed.
Thank you, Dr. Meenakshi. Thank you, Dr. Arumuri. It is a pleasure to be give a talk in Meenakshi College, a college that I have seen during my years in Madurai almost every day. Right next to the bridge. Can you all hear me?
Sir?
Can you hear me?
Yes, sir. Yes, sir.
Okay. Great. Thank you. So it's a pleasure to be giving a talk in Meenakshi College, a college that I have seen almost every day. And I spent my college years in right across the street from Meenakshi College in American College for nearly 5 years, getting my BSc and MSc. And that's a college that I hold very close to my heart. because
move
that's where I got my education. So may I request everybody to mute yourself in case you haven't muted yourself, because I'm hearing some noise, please. Thank you. So what I would like to tell you today about is the kind of research that is happening in my lab. And I will just give one, maybe two examples, depending on the time that we have. If we have time, I will go through two examples, but I will go through just one example. My primary objective today is to tell you about how we are inspired by nature and how we think about solving problems. So in my group, we are interested in responsive materials. This is a phone that I see that iPhone is very popular in India because almost every other Tamil movie that I see, they talk about how fancy iPhone is compared to other phones. But any phones these days, any of these so-called smartphones has this idea of touch sensitivity, meaning if you touch the screen of the phone, you will have you can access information and you can operate the phone, and it gives you enormous flexibility in operating the phone. But if you think more about this really small handheld device and the impact that it has in our lives, this used to be the phone during my grandfather's age. You call an operator and the operator hooks you up to make a phone call, and you have to wait for making long distance calls and everything. And old camera, old clock, and a calculator. All these and many, many more are just packed inside a small handheld device. The information that you get out of a device like this is incredible. And there's a lot of chemistry involved in that. But I'm going to focus on this idea of touch sensitivity or sensitivity in general, okay? Sensitive materials. So there's a lot of chemistry there as well. But if you think about almost any process, there is a inspiration from nature, meaning nature has already developed even more sophisticated chemically responsive systems than man has ever made. And I don't know if you have ever wondered the touch sensitivity of an iPhone and the touch sensitivity of this plant. This plant is called Mimosa pudica, a touch-me-not plant in English. Botanical name is Mimosa pudica. And in Tamil, we call it Thottasiningi sedi. And, as a child, I have definitely played with this plant a lot. And I was always fascinated by it. But I was never taught to be fascinated about the science behind it. And so now I am fascinated about it. And similarly, there are three other things that I'm showing you here. This is a Venus flytrap. This is a plant that eats animals, typically flies. When the flies sit in here, this video was taken with a frog. When the frog touches this plant, the plant closes and the plant ends up eating it's a carnivorous plant. It eats the animal. And similarly, this is also another plant which has a bladder. And if you watch this insect as it crawls inside, and if it touches the lip of that plant, that opening, that mouth of the plant, there is a negative pressure that is created. And that causes this insect to be sucked inside and it'll die. And the plant will eat that insect. And that's the idea. And we will talk about this shark and this fish in a minute again. But these are all touch-sensitive systems. So what we are interested in is the idea is the touch here. When the person touches this plant, it is a macroscopic touch, meaning you can see the touch and the response that you see in terms of the leaves shrinking. It is also macroscopic. But what is interesting is everything that is happening in between has a lot of chemistry and molecular scale events that are happening. So this is the kind of thing that we are interested in. The problem is if we want to make macroscopic processes that we can see and feel are typically millimeter in length scale, and it takes seconds to happen, okay? Whereas molecular scale processes are sub-nanometer or nanometer scale, and molecular scale process also happens in much faster time scale. It happens in nanoseconds. So how do we bridge these processes that are happening in molecular scale with macroscale processes? And how do we generate artificial systems that has these type of macroscopic responses is the question that my research group is interested in. And what you will see is, so in order for us to understand this, we have developed a variety of materials. So I'm sorry, I'm just going to say one thing. Somebody is using their annotation to draw these types of lines in my screen. Can you please not do that? It will interrupt the talk, and I greatly appreciate it if you don't do that. Thank you. So, I have a problem. My mouse got stuck because of that. Give me 1 second, please.
Sir, please unmute your. Okay, sir. Thank you.
It's not muted. It's actually my computer is frozen. Give me 1 second. Okay, I got it back. All right. So when you make responsive systems, there are two types of things. If you think about that, the responsive systems, when you touch, the response happens. The touch is the input, right? The finger touch is the input, and the leaf shrinking is the output. But if you think about, those are inspirations, but let's think about artificial responsive systems that we can make. And let's think about the inputs and outputs that we can have in artificial systems. So in artificial systems that we design, the input can be chemical in nature. It could be pH, redox, non-reactive molecules, or salt, for example, in the form of ionic strength, and variety of other systems. Or the physical, you could have a physical input. Mechanical, temperature, light are examples of physical input. And if you think about the touch, the idea of touch is a mechanical input. And you can also have biological inputs like pathogens, proteins, and DNA, RNA, they all can be inputs as well. So these are the inputs in responsive systems. And if you think about what are the different outputs one could have, what you arrive at is what is the use of these, why do we need to make these materials? So the response could be a transduction event, meaning there is a signal change. So for example, in this system, this I have as a control. This is the sample that I start with. If I add a metalloprotein, the fluorescence completely goes away. But if I add a non-metalloprotein, the fluorescence is retained. That means I have a sensor for metalloproteins that I can develop. So that's a transduction event. Or I could have a molecular release event. So even a capsule, I have molecules inside the capsule. And then when I use a input, let's say light or pH, I can trigger the release of those molecules, and that's a molecular release event. And that could be useful also. So, and similarly, I could have a physical property change. So for example, if I have a surface that is hydrophilic, meaning it likes water, but because of a trigger can change to a hydrophobic surface, meaning it does not like water. And so that's a physical property change. So the kind of use that it has is in a transduction event, you can use examples like sensing and diagnostics, and a molecular release event, you could use drug delivery and self-healing, and a physical property change, you can have self-healing type material, or sorry, self-cleaning type materials. So I want to actually briefly take you through each of these applications so that you can appreciate the kind of materials that why we are interested in these types of materials. So first, the transduction event. I'm going to give you two examples in each of these. So I mentioned to you sensing and diagnostics. So here's an example of a pregnancy sensor. So if a young woman is pregnant, and if they wanted to see at home itself if they are pregnant, the simple device in which you can simply, they deposit their urine, the urine sample will tell them whether when these two lights light up, it means they're pregnant. If there is only one line that comes up, it is not pregnant. It's a very simple analysis. And the reason this happens is because pregnant women secrete a certain chemical, and all we need to do is to develop a sensor for that chemical. And then if we convert that chemical signal into an electrical signal, you should be able to see this, or a spectroscopic signal, you should be able to see whether a person is pregnant or not. And similarly, you could, in this case, there is a tumor here on this person. And if you want to see where exactly the tumor is, if you're able to develop a system in such a way that you are able to make this tumor light up in a different color, and then if you take an imaging of this person, you should be able to figure out where the tumor is so that you can decide, as a doctor can decide whether they need to do surgery or they need to do a medicine, and if there is a medicine, what kind of medicine that they would give to this person. Similarly, you could think about molecular release events. The examples are drug delivery and self-healing. Drug delivery is, I showed you the tumor in that person, and here is a patient, a cancer patient, getting a chemotherapeutic drug. And this drug, when it goes into their body, it needs to be able to specifically go to the tumor and not to other parts of the body. And right now, there are actually the medicines that people use, they actually go to all parts of the body. And that's why women who go through, or anybody who goes through cancer therapy, suffer weight loss and they lose their hair. And that's why this lady is wearing the head cover, because she's probably completely bald and she does not have any hair in her head because of the medicine. And those are all side effects because these molecules go after all the cells instead of just the cancer cell. So if you're able to deliver drugs selectively to a target, it has an advantage. And similarly, so what we need is in terms of our responsive materials, if you have a capsule, a nanocapsule that has these drug molecules, but only in the presence of only when it goes near the tumor, it opens up and releases the drug, you have this opportunity to be selective. And in our group, we are actually working on it, but we're not going to talk about that today. Similarly, you can use these molecular release events for self-healing materials. So what I'm showing you here is an airplane. So imagine somebody's in an airplane and the wings of the airplane cracks. If there is a crack in it, it is a scary thing for everyone because everybody will be scared because we don't know whether we are going to be able to safely land or not. But in those airplane wings, if we also design the material in such a way that it is self-healing, meaning the mechanical stress of a crack. The crack actually causes a mechanical stress, and the mechanical stress releases something that heals the crack. And you may be able to do it only once, but that once is enough, because if it heals the crack, you can actually safely land, and then you can decide how to fix the airplane. And you might imagine these all looks like science fiction, but the first step towards this technology, there is actually, based on these self-healing materials, there is a self-healing paint that is available right now in stores in this country, where you can paint your walls with this paint. And if a child uses a pencil or a pen and cracks the paint, the paint actually self-heals itself. And so those are the types of things that, but to make an advance that ultimately self-heals planes, there's a lot more that we need to do, and we are working on that. Similarly, a physical property change. I mean, here are two examples. So when you wear a raincoat, the raincoat is protecting you from the rain, but so the water doesn't go in and touch your skin. But at the same time, that same raincoat should be able to make you feel comfortable when it is not raining, because for you to feel comfortable, the moisture, the sweat that you get out of your body, as well as our skin breathes, the air from our body needs to exchange with the environment. If we don't, we feel very uncomfortable. That's why we feel comfortable in cotton clothes in hot summer. So if we can develop a material in such a way that as soon as it becomes wet, the pores close in such a way that it doesn't allow water inside. But in the absence of water, you will be able to freely exchange moisture and air. Then you will have a responsive raincoat, and that's not done yet. Similarly, let's say you have police or our army goes to a site and where there is a chemical weapon. They know that a foreign country is using a chemical weapon. They need to be able to protect themselves. So if they wear these clothes, can we design this material, the same idea, that in such a way that they're comfortable, but when they're exposed to a chemical weapon, those pores will close in such a way that the chemical weapons cannot come into contact with their skin, so that their lives are protected. They are protecting our country, and can we design systems to protect them? Is the kind of things that we can design. So we are working on these types of materials. But if you think about so I told you about these inputs, and I told you about these outputs, and what are the advantages of these, and what are the different applications that we can work on. But from a chemistry perspective, so what I'm going to do is to dig into the details and say how we are going to design chemical materials that does these types of response. And I'm going to give you a very simple example so that we will all understand. So from a chemistry perspective, we're going to develop structure, and we're going to correlate function. So the output is the function. So we are going to target a specific function. And we are going to think about, at least in one example, how are we going to design structures in such a way that we can get this function out? And that is what we are going to work on. So let's come back to this plant, the Mimosa pudica, touch me not plant. I told you that the touch is macroscopic and the response is macroscopic, and everything that happens in between is molecular. So in this case, the thing that we are going to mimic is the following. So if I have a capsule, so what happens in this plant is that when you touch, if you imagine this to be a cartoon of a cell, the plants also have cells, and plant cell. And when the person touches, the mechanical force of the touch causes these protein molecules in the membrane to expand because of the touch. And that causes these molecules that are trapped inside to leak out. And that creates a sequence of processes that ultimately results in this type of a response. And similarly, I told you about this fish that I will also tell you about. And this is exactly the process that we are going to mimic. So I want to tell you a little bit about this, just for 2 minutes. This fish is called a hackfish eel. And so you see that fish more close up in a photograph here on the right-hand side. But if you focus on the left-hand side for a minute, what you see is a shark is coming from the back, and it is attacking this hackfish. And this is actually an underwater camera that you can see. So when the shark bites this fish, what happens is if you closely watch the mouth of the shark, there is a gel formation. It rapidly deploys a gel, and you could see this gel in this movie. This person touches the fish, and because of the mechanical force of the touch, the fish releases this gel, and the person can actually get the gel from the hand. See, the whole hand is a gel because the fish deploys this. But the reason it deploys against the shark is because if you watch the shark closely, when it bites this, it cannot breathe because it deploys this gel, and the shark cannot close its mouth anymore, so it suffocates. So because it cannot breathe, it swims away, and it doesn't complete the bite. It does not kill the fish. So it's a self-defense mechanism. So this process is very similar to what I told you about the touch me not plant, where you have a cell. When you squeeze the cell, it releases these threads and skeins, and it forms a network, and that becomes what is called a hackfish slime or the gel. So instead of this mechanical touch, being chemists, we want to use a different kind of input. So what we are interested in, and I'll tell you how we designed this molecule, is we want to make a nanocapsule just like the hackfish has. And we want to have molecules inside this, inside these systems that will be deployed to make a gel. But the trigger that we are going to use is light and not mechanical trigger. And we want to see whether we can do this. And the reason why we are interested in using light is when you shine light, you can use space control because you can use a sharp light like a laser pointer. You can direct light to a specific location, and you can spatially and time-wise, you can control gel formation. Ultimately, that's the idea, right? That's why it's interesting. But we have to develop the chemistry first. And I want to show you and tell you what is the type of chemistry that we thought about in order for us to make this, okay? So the process that I need to tell you about is I need to know how to make this nanoparticle or nanoassembly, if you like. I need to know how to encapsulate these molecules inside. And then I need to design the system in such a way that when I shine light, this capsule bursts open. And when it bursts open, there has to be information in the system to say that if it opens, it has to make a gel. All these processes I need to program into the system. So in the next few minutes, what I'm going to focus is about how we designed this system. So first, let's think about how to make this nanoparticle, okay? So the way we did this was we took a polymer, and then on the red color that I have here, these have negative charge in it, okay? And I'm going to also take another polymer, and this polymer is going to have a positive charge in it. So naturally, when you think about the red color, and the anionic structure, that is the negative charge, and the cation, which is a positive charge. And when you mix them together, they will interact with each other. And because they interact with each other, we develop the conditions. I mean, not all the time it will make a nano assembly, but we developed the conditions in such a way that these will make nano assembly. Now, I've also put in this star in this polymer, and we will come back to why this is here in a second. And that has a specific purpose as well. And we will talk about that in a second. So why does this make this nano assembly? And this is because of what is called multivalent interactions or polyvalent interactions. Multivalent interactions means that if you have a molecule that has multiple contacts with another molecule that also has multiple contacts, your interaction strength will be much higher, okay? A simple example, again, not in nature, but in this type of multivalent interactions is something that you have used in your life. If you use a Velcro, whether it is in a shoe or whether it is somewhere else, the Velcro has two parts, the strap and the other part of the strap where you can glue the things together. And the reason this attaches to each other is because if you take a very, very small part and if you connect that two material, the interaction strength is actually very, very low. But if you have, because you have multiple contacts from both parts of this, you have a strong interaction. That's why you have you are able to glue them together, and then you can strip it apart and you can re-glue it, right? So this is an example of a multivalent effect. So that's what we are using in this system to make this nano assembly, because this interaction strength is very strong. Okay, so next, what we need to do is to incorporate these gas molecules inside. And so, we can, because the environment inside is different, we know how to incorporate these molecules inside, and I'll show you the evidence of that in a couple of minutes. So then the question is, so we have made these assemblies, and we know how to encapsulate this, and I'll show you in a second. But how do we break it up? And I told you that this multivalent interaction is important to make this, right? So the idea is, if I break the multivalent interaction, I should be able to decrease the strength of the interaction and therefore open up the caps. And that's the idea. And that's the reason we have this star here. So the idea is, if I break the star, somehow, if I break the bond between the star and this polymer, I should make this polymer go into a monomer, meaning a small molecule, and it will not be strong anymore. So this is similar to, so if I have a polymer like this, and if I have the star is illustrated here with this attachment, and if I provide light on any other stimulus, and that stimulus causes this molecule to break, and that bond breaking should somehow trigger this polymer to become an individual monomer. So this is like a domino effect, as people call it, a domino effect or the cascade effect. And I will show you the chemical reaction by which this happens as well. So then we also need to make the gel. So when we release the system and we break open the capsule, we have to make the gel. And how does that happen? We'll also talk about that. So now we'll come to the molecular design. So I told you different features that we need to have. So for example, in this polymer, I won't go through the synthesis of this polymer, but we made this polymer. And I showed you the star and this red color negative charge. The negative charge will be based on this carboxylic acid. And the star will be based on this orthonitro-benzyl functional group. And this has each of them. So this is light sensitive, because remember, we wanted to be making light sensitive. This bond will break because of light. And this is a negative charge that we have on this polymer. And this is going to interact with a positively charged polymer. And this is a positively charged polymer that we have. There are multiple. When I put this bracket an N, that means there are multiple copies of this. And this is a polymer that we can buy from chemical companies. So we simply bought this and we didn't make this polymer. And when you mix these two polymers, we have made this we make these nanocapsules, and I will show you, and then we incorporate molecules inside. So I'll show you the rest of the process in a second, and so how we make the gel also in a second. So how do we break this open? What is the molecular mechanism behind it? So I showed you the structure. We have this carboxylic acid, if I didn't put the colors in here, and this is the star part. And when I told you, when I shine light, this bond breaks, and you make this functional group and this nitrosobenzaldehyde. Okay, it becomes NO. And this structure here, this functional group is unstable, so this will go away as carbon dioxide. And I'm just pushing the arrows to show you how the cascade happens. And when the cascade happens, this polymer breaks up into this really small molecule. It's an unstable molecule, and carbon dioxide and this molecule. And this molecule reacts with water to ultimately make final stable product, this product, very quickly. So these are all, of course, assumptions to say that this is what we are going to make. But does this really happen? We indeed characterize these molecules by NMR. So we know we made these molecules independently, so we know how this molecule is supposed to look. And we know the NMR of this polymer. So if you take this polymer and if you shine light, and if you monitor that signal from the polymer over time, you see that that signal is going down with time. And similarly, if I look at the product NMR, and those signals are increasing with time. And that's how we know that we are converting this molecule to this molecule with time. So we can actually get kinetics of this structure. And so we can actually look at time and how fast we degrade, and we can do all the degradation kinetics that we want. And I won't go through the details of this. So the other thing is I told you that this makes a nanoparticle, right? It makes this nanoassembly. And how do we know that? So, in fact, we characterized it. So when we mix these two polymers, it makes this nice assembly of about 300 nanometers in size, so 200, 300 nanometers in size. So I always tell the students that a picture is worth 1,000 words. So we did a microscopy of this. This is a transmission electron microscopy of this assembly. And when you take this transmission electron microscopy, you see that we're actually able to make these nanoassemblies. And if you look at the scale bar here, these assemblies are about 250, 300 nanometers in size. And this is the zoom in of this to show you that we made actually a capsule. And inside this capsule, we are able to put in the molecules that we want to put in. Remember, we want to characterize that. So we know that we chose this dye in such a way that this is a dye molecule that we can take spectroscopy in. And the fluorescence, if it is inside this capsule, the fluorescence will be reduced. And if it is outside the capsule, it will be more fluorescent. And we could tell that these are inside because when the molecule is inside the fluorescence is reduced. But what is also interesting is when I told you that we will use light to break it open. And when we break it open, these molecules should be released. And if it is released, the fluorescence should go back up. And that's in fact what happens. When you shine light, the fluorescence goes back up. And that's an indication that we're able to break open the capsule and release these systems. Finally, I need to show you that we are actually able to make these gels upon shining light. So in this case, what we did was we encapsulated instead of a dye, we put in enzymes, okay? And this enzyme, what it is supposed to do is and then in the solution, in the bulk solution, not inside the assembly, we have this molecule. And when we have this molecule and the enzyme and they see each other, in the presence of hydrogen peroxide, this polymer will extensively cross-link. It'll make a network, and that network will make a gel, and that's the idea. Okay, so instead of in terms of making a gel, so we, instead of the dye molecule, now we put in an enzyme. We encapsulated an enzyme, and then we wanted to see if this idea of making the gels work. So in fact, it does. So people call this an inverted vial test. So before I shine light, if I take all these, the mixture of all these compounds, my nanocapsule with the enzyme inside, with this molecule outside, if I don't shine light, and I put it in a bottle, and if I flip the bottle, because it's just a solution, it'll just fall down, right? Because water flows. This is an aqueous solution, so it's water. But if you see the same vial or a bottle with, when you shine light, it makes a gel. And because it makes a gel, the gel stays up here. You can see the gel here, okay? And then it does not flow. And we also characterize these gels using what is called rheology. And so we know that we are characterizing this not by just taking photographs. So we do all the precautions to make sure that we characterize it properly. Okay, so this is the this is the idea, right? This is one example of a molecular design where we were inspired by nature to look at how the shark bites this fish, and this fish has its capsules, which it deploys rapidly and makes a gel in response to this mechanical input of a shark bite. But we are interested in now designing systems in which a light trigger can cause this gelation. Would we be able to make it? And we did. And we are now thinking about what are the other uses that we can have for this material, because we developed the chemistry first. I am about 43 minutes into my talk. So what I'm going to do is to spend about 7 minutes or 5 minutes or so to tell you another story, just the inspiration, to tell you about another application that we worked on as to why this is interesting, but I won't go through the details, so that we will leave some time for questions before we end this talk. So another example that I want to tell you is what I would call as a need-driven motivation, not driven by nature and our fascination for can we create artificial materials like this, but to actually think about what we can do in terms of solving problems that is required. And this is an interesting problem. It is different from the other problems that I showed you. So I don't know if in India we have this, because in McDonald's or whatever, because in India we always get cold drinks from the refrigerator directly, from the fridge directly. In the US, many times when you go to a restaurant, when you go to a hotel, what they do is they take a cup and they first get ice from this, and when they put ice in their cup, and then they get the drink will flow from any of these, whether you want Pepsi or Coke or a Diet Pepsi or whatever you want, and that's what this machine does. So we had an interesting problem that the Pepsi company proposed to us. And the problem that they proposed to us was that would we be able to release molecules at low temperature, but at the room temperature, the molecules should not be released. So if you think about why that is, why is this interesting, is because what they wanted was this drink is normally stored at room temperature in the fountain. It's not cold. And it is made cold because the customers put ice. The Pepsi has a lot of chemicals in it, right? I mean, to make you feel good. And one of those chemicals is flavor. It has this nice smell to it. and it makes you feel good. And people, food scientists, do a lot of research about this. And the problem is those chemicals degrade very fast with time over, let's say, a 2-month period or not, or something. And therefore, from manufacturing to putting it in somebody's store and you getting that drink, within 2 months, the quality of Pepsi is starting to lose its original flavor. And so the quality goes down. And they want to increase the quality. So the idea is, would we be able to encapsulate those flavor molecules inside these in such a way that they don't release at room temperature, but at low temperature, it will release? When they say this problem, as a scientist, we ask this question, right? Can we make a guest release faster at low temperature? And that is really a very difficult problem, because the question is, can we make a process more dynamic at lower temperature? And that is counterintuitive, because we know this equation called the Arrhenius equation, right? People will say, meaning what you learn in your books, you don't use it, really. But that is not true if you think about and if you know what the concepts that you read means. And so if you think about Arrhenius equation, it tells you that the rate is directly proportional to temperature. Okay, even though it's the denominator, because of this negative sign and this exponent, it's actually directly proportional to temperature. That means the process can go faster at higher temperature, but not faster at lower temperature. But still, we have to do this. So how do we do that? And we have designed a system, and I won't go through the details as I told you because of time, but I would simply tell you that there is a process called lower critical solution temperature process, or cloud point temperature process in polymers, which we used for this system in such a way that we were able to design such a system. And as I mentioned, I'm not going to go through those details, but I'm going to stop here. Before I stop, I want to make sure that I acknowledge my students. Maybe I'll show you this one data to show you that this is really. So here's a system in which at 4 degrees, at 37 degrees, the system is completely not happening at all. It doesn't progress. At 25 degrees, it is happening very slowly. And at 4 degrees, instantaneously the process happens, the molecular release process. So we can actually, our idea in the system actually works. So I will stop here, and I want to acknowledge the people who did this work. This is an slightly old photograph, about a year or year and a half old, because we were going to take, our weather gets better here, our temperature gets better here around March and April, and then COVID happened. And definitely we are not socially distanced here, so we haven't taken a picture. This is a while ago. This is my research group, my students, mostly PhD students, and there are a couple of postdocs and a couple of undergraduate students also here, but mostly my PhD students. And they are a wonderful bunch of students who did this work. The work that I told you today was done by this one student. And I just want to tell you, as I told you, it was just a small example of what we did, of many things that we do in the group. This particular work was done by this student, and this was actually only one chapter in his thesis. And so it was he did a lot more work. And all these other people do a variety of other things. I showed you in the beginning, we work on a range of systems from self-healing materials to cancer therapy. So these students are working on a lot of different projects, and I didn't have obviously time to tell you about all those things. I just wanted to focus on one topic and tell you in detail so that you will understand and hopefully be inspired to pursue higher education, go for a PhD and achieve greater things. Meenakshi College is a college for women. I think in India, we need women leaders a lot more. In all the big position in scientists, it's occupied by men. We need more women leaders, and you can do it if you put your mind to it. And that's one of the reasons in my research group, if you look at the number, we have almost equal number of women and equal number of men, because I want to encourage both men and women to pursue science, to become future scientists. So I just saw a movie called Hero this weekend by Sivakarthikeyan. I encourage people to see it, about how you need to understand and study, and not just memorize to get grades. It was that point, although there were some mistakes in the chemistry that they talked about in the movie, the idea itself in the movie was really good, and I strongly encourage people to see it and be inspired by it. So this is a topic that I told you about. Thank you again, Dr. Meenakshi, Dr. Arulmozhi, for having me here. It was also nice to hear that Dr. Arulmozhi was my super senior in college. So happy to be here, and I'll be happy to answer any questions. Thank you so much.
Thank you, sir. Thanks a lot. Your presentation is very excellent. Sir, I have one question, sir. What are the techniques we adopt to measure the cavity size of the host molecule and size of the guest molecules, sir?
So, yeah, very good question. So the size of the guest molecules, let me, the cavity size that we can measure, we cannot measure, but we can estimate. Maybe
estimate. Okay.
So if you look at this, we can know the density of our polymer and the number of polymer chains that we have, and then we can calculate the shell thickness. And so if you calculate from the density and from the shell thickness, we can estimate the pore diameter in these. And then the guest molecules, because we know what guest molecules we are putting in, we know the size of the guest molecules, because we are not making guest molecules, we are just putting them. And so, but we have put in guest molecules. The dye molecule that I showed you in the next slide here, this is a small dye molecule, like a typical organic molecule, molecular weight of about 450 or something, around 400 or so. And the enzyme that I showed you, that results in the formation of the gel, I just illustrated it here as the structure. That enzyme molecular weight is about 25 pounds. So that's a big guest molecule.
Thank you, sir.
Sure. Any other questions? So, Dr. Meenakshi, I know that somebody might be posting questions in the chat. So I'm hoping that you can read it for me, or because I'm not able to see the chat.
Yes, sir. Yes, sir. Of course. Yes, sir. Yes, sir.
If you want me to answer, so you can choose the questions and ask also.
Sir, there is one question, sir. How to become a part of your PhD group?
So the way, yes. So the way you can, when you, so first of all, you have to get admission in the university. That is not in our, in the individual professor's hands. it is up to the
Okay, sir.
department. Can I ask everybody to mute yourself if you're not talking, please? Can the host
Sir,
mute someone?
please mute, sir, please. Participants, please. Sir, please mute, sir.
நீங்க host ஆனீங்கன்னா you can mute yourself. Mute the person who is talking. Okay.
Yes, host.
Okay. So thank you. So the way you apply to the university is anybody who is applying to the university needs to first take TOEFL and GRE. TOEFL is an English exam, so you need to demonstrate English capabilities, and then you also need to take GRE. So if you take short TOEFL and GRE, and if you succeed in those, if you make a good score, and then you also have good recommendation letters from your teachers and good marks in your class. Plus, most of the time, the students who apply to our department and are successful, they already have some research experience. So people who are interested in PhD, what I strongly encourage is during summer or any holidays you approach the local research institutions and ask them for a chance to work as a volunteer, where you go and do some work and learn about research. Because students from all over the world apply to our program, and they really have a lot of research experience. So you should also try to get some research experience. And once they come into the department, we decide which student works in which group. So that's the kind of steps that you need to take in order for admission in the department and then in the research group.
Sir, one more question in the chat box, sir. Is there any relationship between the input in tissues and DNA or RNA?
Input in the tissues and... Can you complete the question, Dr. Meenakshi? I'm sorry, I didn't hear it.
No, sir. He just wrote like this. Is there any relationship between the inputs in the tissues and DNA or RNA?
Oh, I see. Yes, I mean, the thing is, all our functions, in our cells, all the functions of small molecules, functions of all the molecules have inputs. So, for example, when we need a protein in our cell in order for it to function, we need to give instructions to the cell for the DNA to express that protein, to make that protein, because the information on to make a protein is actually stored in DNA, and it uses RNA to make the protein. And so if we don't give that signal somehow, there is a chemical signal that goes to the nucleus, which is where the DNA is stored, and it says, can you specifically make this protein? And so that becomes the DNA then instructs and transcribes RNA, and then RNA translates to proteins.
Thank you, sir. Thanks a lot. Now
Sure.
it is the time for vote of thanks. It is my honor and privilege to propose vote of thanks behalf of the Postgraduate Department of Chemistry, Sri Meenakshi Government Arts College for Women, Madurai, in this enthralling day. Let me first of all start by giving glory to the Almighty God for making this occasion as a resounding success. First and foremost, I thank our resource person, Dr. S. Thayumanavan, Distinguished Professor of Chemistry, University of Massachusetts, ESA. Your presentation is very excellent, sir, and it is an eye-opener for the future research. You have explained clearly about the inclusion chemistry. Your research is fully application-oriented, which is beneficial to the society. I, I want to express my personal thanks to Dr. Thai for his immediate response to our invitation amidst of his busy schedule without any hesitation. Thanks a lot, sir, for your service rendered to our department and our college. Thank you. I thank our principal, Madam Dr. S. Vanadi, for her constant support in all our endeavors. I extend my gratitude to our HOD, Dr. J. Arulmali Ma'am, for her contribution and guidance in all our efforts. My heartfelt thanks to Mrs. B. Mariamal Madam, Dr. R. Muthuselvi, Mrs. D. Renuka, Dr. P. Shanti for their support. I thank all the participants who will participate in this webinar. Thank you. Once again, I thank you all. Thank you. Sir, thank you, sir. Well, 2 days
Thank you, Dr.
immediate
Meenakshi.
accept
Thank you.
ரொம்ப
It was
thanks,
such a
sir.
pleasure coming back
Thank you.
to Madurai, being in Madurai. Thank you. Okay, bye.
Thank you, sir.
Okay, bye-bye.
Now you can quit, sir. Thank
Okay,
you, sir.
thank you. Okay, bye.
Participants, the certificate distribution will take 2 days to 3 days. Participants, dear participants, thank you for your participation, and the certificate distribution will take 2 to 3 days.
அப்படின்ட்டு யோசனை இருக்கு. அப்பதான் அவங்களுக்கு கொஞ்சம்